In just 10 hours of pointing at the night sky, a single telescope found more asteroids than most of the world's observatories combined managed to find across several entire weeks. That's not a typo. 10 hours. Thousands of space rocks nobody had ever cataloged before, several of them close enough to Earth to genuinely matter for planetary safety. And here's the part that should really grab your attention. That was just the warm-up act. What this instrument has done since then is even stranger, even more staggering, and honestly hard to fully wrap your head around the first time you hear the numbers. Stick around, because we're about to walk through exactly what happened, and if you want to keep up with every new discovery this telescope makes going forward, go ahead and hit follow right now before we dive in. The instrument behind all of this is called the Vera C. Rubin Observatory, and it officially opened its eyes to the public on June 23, 2025. It sits high atop a mountain called Cerro Pachón in Chile, nestled inside the Atacama region, widely regarded as one of the driest, darkest, and most consistently clear patches of sky found anywhere on the entire planet. That location wasn't picked at random or for convenience. Almost no rainfall ever falls there. Light pollution is nearly non-existent for hundreds of miles in every direction. And the air itself sits remarkably still, meaning it distorts incoming starlight far less than the atmosphere above most other locations on Earth. It's exactly the kind of environment astronomers dream about when they're trying to squeeze every last drop of clarity out of a telescope that never leaves the ground. For most of the last several decades, the dominant belief in astronomy has been that if you truly want the sharpest possible view of the cosmos, you need to escape Earth's atmosphere entirely, which is precisely why observatories like Hubble and the James Webb Space Telescope were launched into orbit and beyond in the first place. Ground-based telescopes have always had to fight against atmospheric blur, shifting temperature layers, humidity, and even faint distortions that are invisible to the naked eye but painfully obvious to a sufficiently sensitive camera. The Atacama Desert largely sidesteps that entire problem through pure geography. The combination of extreme altitude, bone-dry air, and a location isolated from any major city's glow creates one of the most stable, transparent columns of air anywhere on the planet's surface, which is part of the reason this same general region already hosts a cluster of the world's most important telescopes. Building here allowed engineers to pair an already exceptional natural setting with a 3-mirror optical design and a fully automated nightly scanning system, together minimizing the atmospheric limitations that still hold back most other ground-based observatories elsewhere in the world. Here's what genuinely separates this observatory from almost everything that came before it. Most telescopes are built to zoom in tight. They pick one small patch of sky, a single galaxy, a single star cluster, and stare at it with incredible precision, extracting as much fine detail as possible from a very narrow slice of the universe. The Rubin Observatory does almost the exact opposite. Its entire design exists to capture enormous swaths of sky in a single shot, then repeat that process night after night, across 10 straight years, building something closer to a continuous time-lapse film of the entire visible universe rather than a curated photo album of individual objects. At the heart of this machine sits the Simonyi Survey Telescope, built around an 8.4-meter primary mirror using a 3-mirror design that's unusual even by observatory standards. Behind that optical system sits the actual camera, and this is where things get genuinely absurd in scale. It's the largest digital camera ever constructed for astronomy, roughly the size of a small car, weighing close to 3 tons, and capturing images at 3.2 billion pixels per shot. For comparison, most phone cameras today shoot somewhere between 12 and 50 million pixels. This camera captures more than 60 times that figure in a single exposure. One picture from this telescope covers a patch of sky wide enough to fit roughly 40 full moons lined up side by side. To gather an equivalent amount of coverage, a telescope like Hubble would need to take thousands of separate images and painstakingly stitch them together piece by piece. The engineering behind that camera really deserves a moment of its own because it isn't simply a scaled-up version of a normal camera sensor. Inside sits an array of nearly 190 individual sensors, each one meticulously calibrated so that when the images are stitched together, the seams between them essentially vanish, producing one seamless picture instead of a visible patchwork. In front of those sensors sit 3 enormous lenses made of fused silica precision ground glass, one of which holds the distinction of being the largest lens ever manufactured, specifically for astronomical use anywhere in the world. Together, these lenses correct for distortion across the camera's unusually wide field of view, which matters enormously for a survey instrument like this one. Without that correction, a star sitting near the edge of the frame would appear smeared or warped compared to one sitting dead center, which would badly undermine the precision. This kind of large-scale survey depends on entirely. The camera can also swap between different optical filters using a robotic mechanism, letting it capture ultraviolet, visible, and near-infrared light in rapid succession, with each wavelength range revealing different physical properties of whatever it happens to be observing, from the surface temperature of a distant star to the chemical composition of a drifting gas cloud. This really isn't a camera in the traditional photography sense at all. It behaves more like a multi-layered scientific instrument, where every single exposure carries hidden information buried far beyond just a pretty picture. Subtle chemical signatures, thermal patterns, distortions caused by gravity-bending light from objects hidden behind other objects, even the faint trails left behind by anything that moved during the exposure itself. Extracting all of that hidden structure from each image is really the entire point of the exercise, far beyond simply producing something visually impressive to look at. If a detail like that already has your attention, imagine what happens once this telescope actually starts working through its full 10-year survey. Go ahead and subscribe now if you haven't already, because the numbers genuinely only get more ridiculous from here. When the observatory finally revealed its first test images to the public back in June of 2025, the scientific community had been anticipating that moment for years. Even so, what came back exceeded most expectations across the board. Engineers and astronomers had run just over 10 hours of test observations, a tiny sliver of what the telescope would eventually spend looking at the sky across its full mission. And in that short window alone, it produced a mosaic that quickly earned the nickname the Cosmic Treasure Chest. This particular image focused on the southern region of the Virgo cluster, the nearest large collection of galaxies to our own Milky Way, and it was assembled by combining roughly 1,000 individual exposures into one seamless picture. Inside that single mosaic sat millions of stars and galaxies. Spiral galaxies with arms stretched lazily across space, pairs of galaxies caught mid-collision, and faint threads connecting distant clusters together like a cosmic spiderweb. Here's the part that really puts the scale of this entire project into perspective. That entire breathtaking mosaic represented roughly 1/120th of 1% of everything the observatory is expected to eventually capture over its full mission. In other words, that jaw-dropping first image was closer to a movie trailer than the actual film. The observatory also released a wide field mosaic capturing two well-known star-forming regions, the Trifid Nebula and the Lagoon Nebula, both located several thousand light-years from Earth, built by combining more than 600 separate exposures, taken across roughly 7 hours of observing time. Normally, when people see images of these nebulae, they come from telescopes designed to zoom tightly into the glowing clouds of gas and dust themselves, filling the entire frame with just that one structure. The Rubin Observatory did something completely different. Because its field of view is so enormous, each nebula appeared as just one part of a much larger neighborhood, surrounded by open star clusters, dense globular clusters packed with ancient stars, and countless other points of light that would normally require an entirely separate observation to capture. It felt less like peeking through a keyhole into one room, and more like having an entire house's floor plan revealed all at once. This single image also perfectly illustrates why this telescope's approach genuinely represents something new. Hubble, one of the most celebrated telescopes ever built, captures roughly 1% of the moon's surface area in a single image when zoomed in on a target. This new observatory captures an area equivalent to about 40 full moons in one single shot, while still keeping enough detail that a star sitting at the very edge of the frame looks just as sharp as one sitting dead center. These two approaches to astronomy aren't really in competition with each other. One works like a microscope, perfect for studying the fine anatomy of a single object in extraordinary detail. The other works more like a wide aerial survey, revealing how that same object fits into the broader structure surrounding it. Used together, they genuinely complement each other in a way neither one could achieve entirely alone. If understanding how these two tools work together is the kind of thing you find genuinely fascinating, make sure you're following along, because we're just getting to the part where this telescope started breaking records for actual scientific discoveries, not just producing pretty pictures. Beyond the visuals, the real headline coming out of that first 10-hour test run was what the observatory found moving through our own solar system. In that short window, it identified more than 2,000 new asteroids, a number that included several classified as near-Earth objects, meaning their orbits bring them close enough to our planet that tracking them genuinely matters for planetary defense. To put that number in perspective, all of the world's combined asteroid tracking observatories working together across an entire year typically identify somewhere around 20,000 new asteroids total. This one telescope matched a meaningful fraction of that entire annual global total in less than half a day of test observations, before its full survey had even officially begun. And this observatory didn't stop there. As its commissioning phase continued through the following months, scientists kept combing through the growing pile of data, and the discoveries kept multiplying. Researchers eventually confirmed just over 2,100 new asteroid discoveries from that initial commissioning window alone, drawn from roughly 340,000 individual detections, collected across about 9 nights of observing, between late April and early May of 2025. Buried inside that dataset was something genuinely remarkable. Astronomers identified an asteroid now cataloged as 2025 MN45, measuring roughly 710 meters across, wider than 7 football fields laid end to end. What made this particular rock stand out wasn't just its size, but its spin. This asteroid completes a full rotation once every 1 minute and 53 seconds, making it the fastest spinning asteroid of its size ever recorded. Scientists studying it noted that for a solid object that large to spin that quickly without simply flying apart under centrifugal force, it would need to be made of remarkably strong, cohesive material, essentially holding itself together against forces that would tear apart a loosely packed pile of rubble. That single discovery, found almost by accident while astronomers were still testing the telescope's basic capabilities, gave researchers a genuinely new data point about how these ancient objects are actually structured on the inside. As the observatory moved further into full operation, the pace of discovery only accelerated further. In a more recent survey period spanning roughly 6 weeks, the telescope logged around 1 million individual observations, resulting in the identification of about 11,000 brand new asteroids, alongside repeat observations of roughly 80,000 previously known ones. Some of these newly identified objects pass close enough to Earth's orbit to be worth tracking carefully going forward. Taken together, these results suggest that over its full planned mission, the single observatory could end up discovering millions of asteroids, comets, and other small solar system bodies, fundamentally reshaping how completely we understand the population of objects sharing our corner of the solar system. There's a genuinely important practical reason all of this matters beyond simple scientific curiosity, and that reason is planetary defense. The effort to identify potentially hazardous asteroids long before they could ever pose a real threat to Earth depends entirely on actually knowing these objects exist in the first place. A telescope capable of scanning huge portions of the sky repeatedly, catching faint, fast-moving objects that previous survey efforts would have simply missed, gives scientists dramatically more lead time to study any concerning object's orbit and rule out or confirm any potential future risk. This observatory is quickly becoming one of the single most important tools humanity has ever built for that exact purpose. If you appreciate a channel that explains why a discovery actually matters instead of just repeating a flashy headline, go ahead and hit that subscribe button now, because there's still a lot more this telescope is built to do, and some of it is even stranger than hunting asteroids. Finding thousands of asteroids was really just a side effect of testing the equipment. The observatory's actual 10-year mission is built around 4 major scientific goals, and asteroid hunting is really only a fraction of just one of them. The second major goal focuses on something this observatory is uniquely suited for: catching transient events, meaning anything in the sky that changes, flares up, or disappears on a timescale, ranging from minutes to just a few days. Because the telescope is designed to scan large portions of the sky roughly every few nights, rather than staring fixedly at one target, it functions almost like a security camera pointed at the entire universe at once. Supernovas exploding in distant galaxies, gamma-ray bursts, sudden stellar flares, and other short-lived cosmic events that earlier telescopes would often catch only after the fact, already fading, can instead be caught right as they're happening, giving scientists a genuine head start on studying them while they're still active. Before this kind of rapid repeating survey existed, catching one of these brief cosmic events required a fair amount of luck. A supernova might ignite and begin fading before any telescope happened to be pointed at that particular patch of sky, meaning astronomers would only catch the tail end of the event, missing the crucial early stages entirely. By scanning enormous portions of the sky every few nights and comparing each new image against everything captured before it, this observatory can flag the exact instant something changes, brightens, dims, or appears where nothing was previously visible. That shift transforms astronomy from something closer to occasional spot checking into something closer to continuous monitoring, catching stellar deaths, violent collisions, and other short-lived phenomena in the earliest moments of their existence rather than stumbling across the aftermath weeks later. Each one of these, caught in progress, gives researchers a far more complete picture of the actual physics driving these events, information that's often lost entirely once an event has already faded past its peak brightness. The third goal involves mapping the structure of our own Milky Way galaxy in far greater detail than has ever been possible before, largely using a specific category of star called RR Lyrae variables. These are ancient stars that pulse in brightness on a predictable, well-understood cycle, which makes them incredibly useful as what astronomers call standard candles, essentially cosmic mile markers that let scientists calculate precise distances across the galaxy. During its very first test observations, The observatory had already identified several dozen of these pulsing stars, and researchers expect that number to eventually grow into the hundreds of thousands across the full survey. Many of these stars sit out in the faint, sparsely populated outer regions of our galaxy, in areas that have historically been extremely difficult to study simply because the stars there are so dim and spread so far apart. By tracking huge numbers of them, scientists hope to trace out faint stellar streams left behind by smaller galaxies that collided with the Milky Way in the ancient past, essentially reading the scars of our galaxy's violent early history written into the positions of these ancient pulsing stars. It's worth briefly explaining why standard candles like these matter so much to astronomers in the first place. Measuring distances in space is genuinely one of the hardest problems in the entire field, because unlike measuring distance on Earth, you cannot simply stretch a tape measure between 2 points floating out in the void. Instead, astronomers rely on objects whose true brightness is already well understood through decades of prior study. Then compare that known brightness to how dim the object actually appears from Earth. The dimmer it looks compared to its known true brightness, the farther away it must be. RR. Lyre stars are especially useful for this because their pulsing cycle is so consistent and well characterized that astronomers can identify them with confidence and immediately calculate a reliable distance. Multiply that single measurement across tens of thousands, and eventually hundreds of thousands, of these stars scattered throughout the galaxy's outer halo, and you end up with something close to a full three-dimensional skeleton of the Milky Way's true shape, including faint structures that were essentially invisible to earlier generations of telescopes, simply because nobody had enough of these markers to connect the dots. The fourth goal is simply to create the most complete and detailed catalog of solar system objects ever assembled, which brings us right back to where we started, all of those asteroids, along with comets and potentially something even rarer. Every so often, an object passes through our solar system that didn't originate here at all, something that formed around an entirely different star, got flung out into interstellar space, and happens to drift close enough to our sun for us to notice it before it continues on its way, never to return. Scientists have only confirmed a small handful of these interstellar visitors in all of recorded history, and each one was discovered somewhat by luck, spotted only days or weeks before it became too faint to study properly. Because this new observatory scans such enormous portions of sky on such a rapid, repeating schedule, it's expected to dramatically improve our odds of catching these rare visitors early, potentially while they're still far enough away to give scientists months of advance notice instead of just days. Researchers studying interstellar objects are genuinely hopeful that over its 10-year mission, this observatory could detect several more of these ancient travelers, each one carrying frozen chemical fingerprints from a completely different star system, offering scientists a genuine physical sample of material that formed somewhere else in the galaxy entirely. The reason earlier interstellar discoveries were caught so late really comes down to exactly the limitation this observatory was built to solve. Older survey telescopes typically covered much smaller patches of sky per exposure and revisited any given patch far less frequently, which meant a fast-moving faint object drifting through on a steep, unusual trajectory could easily slip through the gaps between observations for weeks before anyone noticed a pattern. A telescope covering huge swaths of sky every few nights dramatically shrinks those gaps. Something moving unusually fast on a path that doesn't match anything gravitationally bound to our sun is far more likely to get flagged early, while there's still enough time left before it fades from view to actually point other major telescopes at it, gather detailed spectra, and study its composition properly instead of scrambling to catch a fading, disappearing target. Stepping back to the first of those four goals, the most ambitious one involves mapping dark matter and dark energy, two of the biggest unsolved mysteries in modern physics, by tracking how billions of galaxies are distributed and how they move relative to each other across vast stretches of cosmic time. Scientists cannot see dark matter or dark energy directly, but by measuring how galaxies cluster together and how that clustering pattern subtly bends and distorts light from objects behind them, researchers can begin piecing together indirect evidence about what these mysterious forces actually are and how they behave. To understand why this specific telescope is so well suited to that particular challenge, it helps to know that both dark matter and dark energy reveal themselves only through extremely subtle statistical patterns spread across enormous numbers of galaxies, not through any single dramatic observation. A telescope that can only study one galaxy at a time, no matter how sharply, simply cannot detect these patterns, because the signal only becomes visible once you've measured the shapes, positions, and distances of tens of millions, or ideally billions, of galaxies spread across huge stretches of the sky. That's precisely the kind of task this observatory was purpose-built for. Its combination of an enormous field of view and repeated scanning over a full decade means it will eventually build up a catalog of galaxy positions and shapes on a scale that was simply never possible before. giving physicists their best opportunity, yet to measure exactly how these invisible forces have shaped the structure of the universe over billions of years. Now, all of this scientific ambition creates an absolutely staggering data problem. And honestly, solving that problem might be just as impressive an achievement as building the telescope itself in the first place. On a normal night of observing, the observatory generates around 20 terabytes of raw data, an amount that would overwhelm most traditional data systems almost immediately. To handle it, engineers built a dedicated high-speed fiber connection specifically to beam that data from the mountaintop in Chile directly to processing centers in the United States, where automated systems immediately begin calibrating images, correcting for atmospheric distortion, identifying anything that moved between exposures, and flagging anything that changed brightness unexpectedly, all before a single human scientist has even looked at the results. Over the full 10-year survey, the observatory is expected to accumulate somewhere in the neighborhood of 500 petabytes of data, an amount so large that fully analyzing it will likely take research teams years, if not decades, working long after the observing mission itself has already ended. What makes this even more remarkable is that a significant portion of this enormous data set will actually be made accessible to the public, not just to professional astronomers, with access to specialized supercomputing facilities. Tools have been built specifically to let ordinary people explore these massive, high-resolution images directly, zooming from a wide view containing millions of galaxies all the way down to individual stars and structures, the same way you might zoom around an online map. This effectively opens the door for citizen scientists and curious members of the public to potentially spot something genuinely new themselves, whether that's an overlooked supernova, an unusual asteroid, or some faint object that automated systems initially missed. Given how much data this telescope produces every single night, having more curious eyes looking through it is a genuine advantage, not just a nice educational gesture tacked on afterward. This kind of public access also represents a fairly significant shift in how large scientific projects tend to operate. For a long time, working with genuinely cutting-edge astronomical data required institutional access, specialized training, and computing resources most individuals simply didn't have. By deliberately designing public-facing tools around a dataset, this enormous from the very beginning, the project effectively lowers that barrier substantially, letting students, hobbyists, and anyone with genuine curiosity engage directly with frontier-level astronomical data, rather than waiting years for a simplified second-hand summary to eventually trickle down through textbooks or documentaries. Stepping back, it's worth appreciating just how unusual it is for a ground-based observatory to be generating this much